Okay, hello everyone. Welcome to my presentation with the topic an efficient channel training protocol for channel estimation in double risk aided MIMO system. This is a joint work between my professor and Professor Andre and some other of my colleagues, CPD and Khaled. Here we have the outline for the presentation, and then we go from the introduction to the system model, and then we look at double risk aided MIMO channel estimation, and then we look at the estimation of the single reflection links, and then that of the double reflection link, and then we'll talk about the identifiability and training overhead, and then we look at the result, simulation result, and then the conclusion. By way of introduction, RIS, reconfigurable intelligent surface consists of large low-cost passive reflecting elements that can be configured. The phase shift of this element can be configured to achieve a specific purpose. It can either be configured to have constructive beamforming or destructive beamforming at the interfering user, and constructive beamforming at the desired user. It has given benefits, like this is a picture of the risk here, but here we are looking at moments. So risk can be used to increase the communication range of the system, especially for systems where the direct line of sight between the transmitter and the receiver is blocked by obstacle or maybe tall buildings. Now, research has shown that double rigs have higher passive beamforming gain than single RYX-based system. But however, in the channel estimation for double rigs, it is now complicated because of so many channels. We have additional channels. We have the double reflection links. This is the double reflection link from the transmitter via these two rigs to the receiver, and this single reflection links. In 4 and 5, the channel estimation protocol adopted in them try to simplify this scenario by assuming that these single reflection links are not there. And in 6, the estimation is done by turning off one of the rigs at each point in time and estimating the other corresponding channels. However, to achieve maximum beamforming gain for a double risk aided system, all the channels need to be estimated effectively. So this is our system model. We have the rigs, the double rigs. This is the transmitter, and then this is the receiver, and then G1 to this rigs 1, and then H1 is the first single reflection link, and then G2, H2, another single reflection link, while the T, G1T, and then this is the double reflection link. Now we have L channel training subframes, which is made up of I, J, and K, and then the K is for the training at the transmitter, J is the training of the RX1, and I is the training of RX1, and J is the training sequence subframe for RX2. Now the received signal at the IJK subframe is giving us this, where we see that this is the component 1. It contains 3 components. Component 1 has this single reflection link, like as I've explained before, from G1 to risk 1 and then to the base station. And then component 2 has this single reflection link from G2 to risk 2 down to the receiver. And then we have the single double reflection link, which is from G1 to through RX1, T, and RX2 to the receiver. Now, next, we try to stack up the transmit training symbol, the pilots, for the K measurements, and then we have this Y bar measurement matrix where we have shown that this X is the stacking up of the measurement training pilots, sorry, and then this Y bar is the column-wise stacking of these Y measurements. Then we try to do right filtering by assuming that our training sequence at the transmitter has orthonormal rows, that is, the X times X summation is equal to identity, and with that, we now perform right filtering of this measurement signal above here, and then we obtain this Y, I, J. Our task then is now to how to estimate channels G1, G2, H1, H2, and T from these measurements. Now, the trick we adopt in this work is to assume that the RYX we have, each of the RYX can have two phase shifts. That is in state 0 and state 1, where there is a 180-degree phase shift between the two states. And then this is the trick we adopt to separate these three channels in the receive signal. So the measurement with respect to these two states is given here, where this A and B can be either state 0 or state 1. So we start by estimating the channels that are in component 1. In component 1, we have the channel G1 and H1, which is shown here. How do we estimate these two channels? So first, we perform a two-stage training procedure. First, in the first stage, we fix a beam in RS2. We fix one beam in RS2, and then try to sweep through all the beams of RX1. Then in the second, the measurement obtained is given as Y00 IJ.0. Here we can see that the two rigs have the same, are in the same states, state 0 and state 0 here. Then in the second state, what we now do is to change the state of the fixed beam in rig 2 and then repeat the sweeping through the beams of RX1. As shown in this figure here, RX1 still maintains the state of 0, while RX2 is changed to state 1, and then we sweep the beam. And then we note, because of the 180-degree phase shift trick that we employ, that this identity holds. So we have the obtained measurement in this context is now Y01 IJ0. Then, because of this trick that we use, we combine the measurement, that is the Y00 plus Y01, and then we have these two, we have this measurement matrix YI. We can see that this YI solely depends on only RS1. We have used the trick to separate and eliminate the effect from the other RYX, right? Then with that, we can write this measurement matrix as a three-way tensor, as we have shown on the board, which is solely dependent on RX1. And then with that, we can then estimate channel G1 and H1. So we define, for the measurement tensor in the previous slide, we defined the following unfoldings. This is the first mode and the third mode unfoldings of the tensor that we defined before. And then to estimate H1 and G1, we use this algorithm 1 here, where we try to use least square categorical factorization. Then we obtain H1 and G1 in a sequential order until the algorithm converges. So moving forward, next we try to estimate the channels in component 2, which we have shown in red, the channel from the transmitter to the RS2 and then to the receiver, which is this component here. So we use the same trick, but however, in this case now, we fix a beam in RX1 and then sweep through the beams of ROS2. And in this first stage, like we did before, both ROSs remain in the same state 0. And then we obtain this measurement matrix, Y00. It is important to note at this stage that this measurement matrix, we have it already, so we don't need to repeat any training here. We have measured it before, so we just use it to save cost and training overhead. Then in stage 2, we switch the state of the beam that is fixed in RS1 and then sweep through all the beams in RS2. And then similarly, we have this condition because of the 180-degree phase shift in the phases of the RYX. And then we have this measurement matrix Y10. And then similarly, like before, we combine these two measurement matrices, right? And then we obtain Y of J, Y that is the measurement matrix that solely depends on RYX2 alone. And also, we can write this as a three-way tensor, just like we did before. Then using the unfoldings of this tensor, we can easily estimate channels H2 and then G2. So we leave out that we use the same algorithm as before to estimate channel G2 and H2. So next, we try to estimate the channel in component 3. And in component 3, we have only the channel between the two RYXs, right? That is the channel matrix T. And then to do that, we sweep through for every beam in RS1, we sweep through all the beams of RS2. And then if we do that, we obtain this measurement matrix. However, we subtract the effects because from this, in this received measurement matrix here, we have estimated H2, G2, G1, and H1. Therefore, we subtract the effects from this receipt, just like a successive interference cancellation. And then we have this Y hat, right? Now, this approximation sign is due to the estimation error in this previously estimated channel. That is why we have this approximation sign. Now, this Y hat measurement matrix can be arranged in a four-way tensor that has a nested Prafak model. Here we try to show this. What we do here is to concatenate this measurement matrix in the second dimension of a three-way sensor to obtain this. And then this is the Y that has this channel H2, T, and G1 as a nested Prafak model. So what we do is to estimate this T using the fact that the n-mode unfolding of that tensor can be written as one mode of folding of a three-way tensor. For example, this tensor Z, the the one mode unfolding of that tensor is equal to the third mode unfolding of this four-way tensor. And then using this, why this is for the RYS1, and then this theta is RY for RYS2. And then using that, we obtain that the two-mode unfolding of this Z tensor can be written as this here. Yeah, I forgot I have this. As here. And then this third mode unfolding of this tensor B here is given as this part here, and why this remains like this. So we use this information here to go further to estimate the channel matrix T, because we have already estimated H2 and G2 in this and G1, and we know theta can be phi 2 and phi 1, right? So what we have is the vectorization of this second mode unfolding, where this vector is the vec of this, and then we vectorize this using the vec operation, and then we have it in this form, where this omega, yes, where omega is the whole of this section, and then T here is the vec of our T channel. Then to estimate the T, we simply use least square scheme here to estimate the T, and then this is the vec of the answer, the output, to give us the channel matrix T. So successfully we have estimated the required channels, the G1, G2, H1, H2, and then the channel matrix T. Then next we look at the identifiability conditions. From estimating components, the channels in component 1, we have that for the channel to be, for accurate channel estimation in least square sense, we have that the trailing sequence I of the RS1 should be equal or greater of maximum of these elements in this bracket. And then where this MSI1 is the number of elements in the RYX, and then MUE is the number of antennas at the base, at the transmitter, and then MBX is the number of antennas at the base station. Then we have a similar requirement for estimating channels in accurate channel estimation of channels in component 2, where in this context that the J, the number of training sequence in the RS2, should be greater or equal to the maximum of this operation in this place. And then for component 3, we have that I subscript D should be greater or equal to this, or J subscript D should be greater or equal to this. And for effective, for accurate channel estimation in least square sense. And then for the training overhead, assuming that this ID and JD are equal to I and J respectively, then it means that the training overhead required to estimate these channels effectively is given as 3IJK, which is equal to 3L, because this is the number of training subframes that we have. Okay, next we look at our simulation results. So we have the following channel matrices, which this is the dimension of the channels, and then they are all zero mean circular symmetric random variables, just generate them randomly. And then the training matrices are also generated randomly. This is for the RX1, RX2, and the same thing for RX1 and RX2. But now this is for the measurement, for the estimation of T. And then these are for the, this is what we use for the estimation of the other channels. Now we have these simulation parameters. We have 2 antenna elements at the transmitter, 2 at the base station, and RX1 has 20 elements, and then RX2 has also 20 elements. So in our result, in our experiment, we consider two cases. In case one, we consider a situation whereby the training sequences, like I said before, are equal to each one another, 20, 20, 20, 20, right? But then we now also consider case two, where we have lower training sequences for I and J, and then higher for ID and JD. And then what we consider is the mean square error between the channels and the estimated channel and the original channel. Here we have used P to represent, P can be either 1, 2, 3, that is component for component 1, component 2, and component 3. And in component 1, we define this P1 as H1 times G1, and then in component 2, the same thing. However, in component 3, we have H2T G1. Now we have the means as our result. What we demonstrate here in this figure, the cases with straight lines, the resulting straight line are that of case 1, where they are all equal, and dashed line are situation where they are not the same. Now from the result, we see that first, that is beneficiary to have the same number of training, because we can see that this case 1 have a better performance than case 2. And then the estimation of the component 3 has a slightly poor performance in comparison to the components channels in component 1 and component 2 in both scenarios. And this is, as we demonstrated in the previous slide, that is due to the estimation error, because to estimate the channel in component 3, we have to use the estimates of channels in component 1 and component 2 to arrive at that. However, currently we are trying to extend this work and then try to overcome this error propagation due to the estimation error. And then that is the end, and then we have conclusion. We have RIS have been proposed as one of the key technologies for future wireless communication. Like I said, it can tune the wireless environment into a dynamic environment by performing either constructive interference or destructive interference. And then it also has the potential of extending the communication range. And then in the previous work, we have demonstrated that double rigs also requires less training compared to single rigs. Yeah, but in this work, we have proposed an efficient estimation technique for double risk headed system, where we estimated the 2 single reflection links and the 1 single double reflection link using the trick that we introduced. And then, yeah, the proposed technique allows us to extract the measurement of a particular reflection links interference free from the measurement of the other reflection links. And then the provided results shows the effectiveness of the proposed channel training protocol in a double risk flat fading MIMO system. And these are our references. Yeah, and then thank you for your attention.